Our next speaker is Dr. Jeff Elias from University of Virginia. Dr. Elias is a professor of neurological surgery, and his clinical work and research work focuses on movement disorders and epilepsy surgery, and he uses MR-guided focused ultrasound that we heard some about this morning for the treatment of these disorders. And I should say that Jeff grew up in Roanoke in the Star City, and so we're happy that he came back to his hometown to participate in this symposium. Thank you.
Thank you. Yeah, it's very, very nice to be here. It's always great coming back, and now there's really so much exciting reasons to come back here with this great institution. So I'm a neurosurgeon. I'm mostly a clinician, so I'm going to talk a little bit more about the clinical side of what I see. And up until today, really, I was going to talk a little bit more in perspective of precision neuroscience about a disease. You know, I treat Parkinson's disease as one of the problems I deal with from a surgical perspective. After hearing some of the talks this morning, I switched to talk more about a tool that we're using in our practice, which is focused ultrasound. But let me just summarize what I was going to say about Parkinson's disease. I think that Parkinson's disease is a real ideal disease for precision medicine. It's a common neurodegenerative problem, probably second to Alzheimer's. It's a very heterogeneous phenotypic disease. In other words, we see so many flavors of Parkinson's disease. Oh, hey, thanks. Is that better? Better? Sorry? How about that? Sorry. Did you hear the first part of what I said? Yeah, so I think Parkinson's disease is really an ideal for precision medicine. You know, the patients we see come in with a lot of different flavors, or their phenotypes are very heterogeneous. And now we're learning that there's actually a lot of genotypical variety. So we do a lot of treatments, medical and surgical treatments for Parkinson's disease, and patients actually respond, the variety of response is rather broad. So I think it's really an ideal disease to target with precision or patient-specific type of techniques. And we're starting to get more biomarkers for that disease, not only for early detection, but for treatment and therapy. But I'm actually going to switch gears and talk about this tool, focused ultrasound. And before I start, I'm just going to kind of bring you into the operating room to show you what we see. This is a Parkinson's patient. This is going to be a video from our operating room, and it's going to illustrate, I think, kind of the powerful aspects of neuromodulation. Now, this is not going to be ultrasound modulation, but this will be electrical and thermal modulation. So, yeah, could you play that video? And so this is a stereotactic thalamotomy. We're using it. It's a thermal lesioning procedure for tremor. And you can see that this is a very disabling symptom for patients. Impossible to use your hand with a problem like this. This is an older technique where we insert a probe into the thalamus of the brain. And the first thing that we do is stimulate. Can you pause that? And so we're stimulating with 0.3 volts. This is a very low electrical stimulation. And the patient can respond and tell us that they're having some paresthesias in the tongue, and there's some motor activation in the lips. So that really helps give us some feedback about what to do. And then you could play it again. The tremor is pretty good, but there are side effects and so there's a somatotopic organization of the thalamus, just like your cortex, and we know where we are based on that type of stimulation. We can make an adjustment to the probe. And can you pause, please? If you'll notice, we moved the electrode just 1.5 millimeters. That's a very small movement deep inside the brain. And play it again. There's no lesional effect. That's what this is showing. But all of the effect is from the stimulation. So when we start to turn on the stimulation, you can see the tremor stop. So this is a beautiful demonstration, I think, of the power of neuromodulation, or the ability to stimulate specific circuits deep in the brain. And so the last part of this is that we do kind of a moderate thermal lesion, and then a kind of a therapeutic thermal lesion that stops the tremor without side effects. So I just wanted to highlight that. That's the older technique that we use to treat tremor, but it highlights the neuromodulation tool that we can use clinically, and is so important, I think, experimentally as well. So I'm going to show also, this is our focused ultrasound clinical results. So about 5 years ago, we started to use this technology to do the same thing without inserting a probe. And you can see this is the ultrasound transducer. It's shaped like a helmet so that you can focus the acoustic waves to a single point. There's 1,000 acoustic waves that are individually controlled so that we can focus them precisely at the spot. And we use the MRI to perform the stereotactic targeting and to monitor the treatment, so we can monitor the thermal aspect of the treatment, not only at the focus but in the surrounding brain. And then that can cause a small ablation, just like we did with a probe. And you can see that obviously there's a big clinical effect if it's placed in the right position. And then we just published last month our results of a randomized controlled trial from 8 centers around the world, and it's highly statistically significant against sham-controlled procedures. The ratings were done by blinded observers from videotapes. It's a very rigorously conducted clinical trial that was positive and led to an FDA approval of this technology. So now we have the first FDA approval to use this in the brain for people with tremor. The real reason why we were interested in this was because of this clinical problem of tremor, but also we thought that it was an ideal scenario to demonstrate neuromodulation. So we thought that while the patient is in the scanner, undergoing the treatment, they're awake, and then we would be able to see the tremor stop before we did any thermal lesioning or any heating. So that was the idea, because tremor is a very sensitive symptom to modulate. In other words, just a little bit of electrical stimulation, or sometimes just putting a probe and the tremor stops. It's very sensitive. But that was not really what we found. Anytime, we never really saw the tremor stop until we got into moderate amounts of heating. We thought we would see it at really the lowest levels of heating. That wasn't the case. And we would see sensory effects or neurologic effects with kind of mild to moderate heating. So we really didn't see non-thermal or non-invasive neuromodulation. I think we saw evidence for thermal modulation, but not non-thermal. So that led us to go back to the laboratory and kind of investigate, could we use this for neuromodulation? Just to refresh everybody's memory, acoustic energy or ultrasound is a pressure wave that moves through tissue, and it displaces tissue. And when you focus it to a single point, the amount of energy or the amount of pressure at the focus is exponentially more than each of the individual beams. And so that's what we're taking advantage of therapeutically. And so there's high-intensity focused ultrasound where the pressure intensity is a lot higher, and there's lower intensities of ultrasound, kind of the amounts of pressure or energy that you'd think of with diagnostic ultrasounds like echocardiograms or sonograms. So this is using low-intensity focused ultrasound to cause a mechanical effect, not a thermal effect, not a tissue ablation or cavitation, but a much lower intensity where we could actually maybe use the mechanical properties of ultrasound to cause a neurologic change. And so I want to reference this work. This was done here in Roanoke by Jamie Tyler and his group. It was a real landmark paper in our field. I kind of consider this the real beginning of transcranial ultrasound neuromodulation. This was the first time that anyone showed that ultrasound could be transmitted through the human skull not for an ablation, but to modulate the brain. And so they focused low intensity ultrasound on the primary somatosensory cortex, and they were able to alter evoked potentials, especially this early cortical potential, and they also demonstrated some corresponding behavioral changes or clinical effects like changes in two-point discrimination. So this was really, I think, a landmark advance that proved that this could be available in the near future. We tried to build on what they did. We went back to the laboratory, and we have an animal model. It's a large brain animal model. And really what we wanted to do was to see if we could see if we could cause ultrasound neuromodulation non-thermally, non-invasively in deeper brain structures. And so here you can see our animal model. We're targeting the thalamus, just like we do with the clinical procedures. And this was the first thing that we wanted to do. We targeted the somatosensory thalamus. This is the MR thermography where you could see there's no heating. And you can see that we suppress evoked potential about 30% across 4 animals in 6 experiments at 5 minutes. And then it recovered back to baseline at 20 minutes. And so all these animals went on to have histology that showed no tissue damage, no heating. And so we thought this is evidence of non-invasive neuromodulation. The second experiment that we did, and then I'll end up there, is that we wanted to see if we could map the thalamus with this technique. And so we targeted an area that was outside the somatosensory area, and you can see there's no changes on trigeminal or tibial evoked potentials. And then when we focused on the medial aspect of the somatosensory thalamus, you could see the trigeminal evoked potentials changed about 23%, but the tibials did not. And then we moved the focus laterally and altered the tibial, not the trigeminal. These movements are 2 millimeters at a time. So I think it demonstrates very precise spatial resolution for the effect. We demonstrate across several different frequencies our experimental transducer and our clinical transducers. And there's really no histology changes. This is a high intensity lesion, just as a control. And so just to summarize, I think this is going to be a very powerful technique experimentally and clinically. It's transcranial and non-invasive. You can reach deep brain areas where you can't with like TMS and direct stimulation. The spatial resolution is very good, and it's MR compatible. And then we're still in the early stages. There's a lot of refinement to do. I think you could see that. We only suppress the evoked potential by about 25%. We'd also like to be able to augment or enhance the evoked potentials and stimulate areas of the brain. So I think this is the earliest stages, and there's a lot of potential. Thank you.